All right, this is lesson 3.2 for our calculus class. Unit 3 is called Implicit Differentiation and working with inverse differential or derivatives. Blah. Lesson 2 is called Implicit Differentiation, round 2. So we're going to work more with implicit differentiation, particularly implicit differentiation that involve product rule, quotient rule, and chain rule. And let's take a look at that. So if we have an equation in terms of x and y, and it's kind of difficult to solve for y, or we just don't want to, we can use implicit differentiation. So if we want to derive this thing, we'll take the derivative of each side of the equation. So the derivative of 1 is equal to the derivative of 3x cubed plus 2y cubed minus y. So we'll just do power rule for all these, and then chain rule for each time we have a letter. So again, we treat every letter like it's a composite function, so we'll do chain rule with each letter. So the derivative of 1 is just 0, and the derivative of each of these terms, well, the derivative of 3x cubed is 9x squared times the derivative of x, so that's just going to be 1, plus the derivative of 2y cubed. That's going to be 6y squared times the derivative of y with respect to x. And then we're going to subtract the derivative of y, so dy dx. So now our derivative equation, we have an equation that has dy dx in it. So we're going to solve for dy dx. We're going to move the 9x squared to the other side of the equation. We're going to factor the dy dx out. And then we're going to divide both sides of the equation by that remainder 6y squared minus 1. So dy dx is equal to negative 9x squared divided by 6y squared minus 1. There's our derivative. Next example. So this next example is a little more challenging than the last example because of the negative 5xy on the right side of the equation. So we have a product of functions, so when we derive this, we're going to use product rule. So let's see what that looks like. Okay, so we have the derivative of the left side is going to be the derivative of negative 4y is going to be negative 4 times the derivative of y with respect to x, plus the derivative of 3x squared is going to be 6x, and then the derivative of 4 is just 0, so that washes. And then we're going to derive the right side. So we've got, we could think of this as a function negative 5x times the function y. So product rule, the first function times the derivative of the second, plus the second function times the derivative of the first. So negative 5x times the derivative of y with respect to x, plus y times the derivative of negative 5x. Well, that's just negative 5. All right, so now skipping a couple steps here, I'm going to move all of the dy dx terms on the left and all the other terms on the right. So I'm going to add 5x dy dx to the left, and I'm going to subtract 6x over to the right here. And then I'm going to take my negative 4 dy dx and my plus 5x dy dx, and I'm going to factor out the dy dx. And then I'm going to divide both sides of the equation by my remaining negative 4 plus 5x. So dy dx is equal to negative 6x minus 5y divided by negative 4 plus 5x. And again, this tells us this equation tells us the slope of any tangent line given any point on the graph of this original function. All right, here's another example. So this one's a little different from the previous one because we have an actual function inside of a function. So we're going to use chain rule like crazy. So the derivative of the left side is going to be chain rule. So we take 2 times the inside function to the power of 1 less than 2. That's just 1. So just that. And it's times the derivative of the inside function. So times the derivative of 4x squared plus y squared. So we'll put d dx of this guy. The right side is going to be the derivative of x with respect to x. Well, that's just 1. Okay, now, so I do want to derive this one piece right here real quick. So d dx of this guy is going to be 8x plus 2y times the derivative of y with respect to x. Remember, each letter is treated like a chain rule. So it's chain rule for the problem, and then it's also chain rule for each letter because it's implicit. All right, so now you might be thinking, oh crap, do I have to FOIL this thing? And no, we don't. We don't have to FOIL this thing. We got a binomial times a binomial. We're not going to FOIL it. The first binomial does not have dy dx. Remember, our goal is to isolate dy dx. So we're just going to divide both sides of the equation by this first factor. So we're going to get 8x plus 2y dy dx. And it's going to be equal to the 1 divided by the 8x squared plus 2y squared. And so then after that, we're going to subtract 8x from the left side to get the 2y dy dx by itself. We'll get this fraction minus 8x. And then we're going to have that all over 2y. Divided by 2y, then we get our dy dx by itself. So we have this nice, beautiful answer right here. Okay, so takeaways. Implicit differentiation is more complicated to work with conceptually and symbolically. However, it allows us to differentiate any equation, not just ones that can be written as a function.